Hello and welcome to Slow Orbit. Before we begin tonight's journey, take a moment to gently tap the like button, and if you enjoy calm explorations of the universe, consider subscribing to the channel. It really helps the channel continue bringing these quiet voyages through space and time, and as you settle in, I'm always curious to know, where in the world are you watching or listening from tonight? Maybe you're under a city sky glowing with artificial light, or perhaps somewhere rural where the stars stretch across the darkness. Wherever you are, it's worth remembering that the night sky above you is the product of an incredibly long story, a story that began in a universe that once had no stars at all. Tonight we're going to travel back to a time before the first sunrise in the cosmos, before galaxies, before constellations, before any star had ever ignited. There was a period in cosmic history when the universe was astonishingly simple. No glowing nebulae, no spiral galaxies, no brilliant clusters of stars, just vast expanding space filled with thin gas, mostly hydrogen and helium, drifting through an immense darkness. Astronomers sometimes call this era the Cosmic Dark Ages. It might sound mysterious or dramatic, but in reality, it was a surprisingly calm chapter of cosmic history. The universe had already been born in the Big Bang. The first atoms had formed, light from that early moment. What we now observe as the cosmic microwave background, had begun travelling across space. And then, things grew quiet. For millions of years, the universe drifted through a long twilight. Gravity slowly worked on tiny ripples in matter, gently gathering gas together. These ripples were incredibly small, differences in density no greater than 1 part in 100,000, yet they would eventually shape everything that came later. Galaxies, stars, planets, even us. But during this long stretch of cosmic time, none of those things existed yet. The universe was waiting for gravity to slowly pull matter together, waiting for gas clouds to collapse, waiting for the first stars to ignite and bring light back to the cosmos. It's easy to imagine the early universe as chaotic and explosive, but much of its history unfolded at a remarkably gentle pace. Over tens of millions of years, invisible structures made of dark matter began forming a kind of cosmic scaffolding. Ordinary matter followed these structures, drifting into slowly deepening wells of gravity. Gradually, the universe began preparing for something extraordinary, the birth of the first stars. These stars would be unlike most of the stars we see today. They would be enormous, incredibly hot, and made from the simplest ingredients in existence. And when they ignited, their light would mark the end of the cosmic dark ages and the beginning of a new era astronomers call cosmic dawn. But before that moment arrived, the universe spent a long time in darkness, a quiet darkness filled with possibility. Tonight we're going to explore that forgotten chapter of cosmic history, the age when the universe existed before stars, when space was filled with faint radiation, drifting gas, and the slow pull of gravity shaping the future. We'll look at how tiny quantum ripples became the seeds of galaxies, how invisible dark matter quietly built the framework of the cosmos, and how the first stars eventually emerged from this vast cosmic silence. So wherever you're listening from tonight, whether beneath a sky full of stars or a sky where the stars are hidden, let's take a slow step back in time, back billions of years, back before the Milky Way, back before the first galaxies, back to a universe that had not yet seen its first sunrise. Let's begin. For most of cosmic history, the universe has been filled with light. Stars burn across galaxies. Nebulae glow in delicate clouds of gas. Entire clusters of galaxies shimmer faintly across unimaginable distances. When we look up at the night sky today, we are seeing a universe that is bright, busy, and rich with structure. But there was a time when none of that existed. There was a period in the early history of the cosmos when the universe contained no stars at all. No galaxies, no glowing clouds of gas, no cosmic beacons scattered through the darkness. Just space, just atoms, just a faint fading glow left behind by the Big Bang. To understand how this quiet era began, we have to travel back to a time when the universe itself was still very young. Not young in human terms, of course. Even by this point, the universe had already existed for hundreds of thousands of years. But compared to its present age of about 13.8 billion years, this was still the earliest opening chapter. During the first few 100,000 years after the Big Bang, the universe was a very different place from the one we inhabit today. It was extremely hot and filled with a dense mixture of particles and radiation. Light could not travel freely because the universe was packed with energetic electrons and protons that constantly scattered photons in every direction. In a sense, the early universe was something like a glowing fog. Imagine trying to shine a flashlight through a thick cloud of steam. The light bounces around, scattering in every direction instead of travelling in a straight line. For hundreds of thousands of years, the entire universe behaved in much the same way. But the universe was expanding, and as space expanded, the temperature slowly began to fall. Eventually, the universe cooled enough for one of the most important transitions in cosmic history to take place. Protons and electrons, which had previously existed as separate charged particles, began combining to form neutral hydrogen atoms. Helium atoms formed as well, although in smaller amounts. This moment is known in cosmology as recombination. The name is slightly misleading since electrons and protons were not actually recombining from anything earlier. They were joining together for the first time to form stable atoms. But the term stuck, and it has been used ever since. When these neutral atoms formed, something remarkable happened. The fog cleared. Photons, which had previously been scattered endlessly by free electrons, were suddenly able to travel across space without constantly being deflected. Light could finally move freely through the universe. In other words, the universe became transparent. This transition occurred roughly 380,000 years after the Big Bang. In cosmic terms, it was the moment when the universe experienced its first true clearing of the skies. The light that was released during this event has been travelling through the universe ever since. Today we observe it as the cosmic microwave background, often abbreviated as the CMB. It is the oldest light we can see, a faint afterglow from a time when the universe was only a tiny fraction of its present age. Although this radiation has been stretched by cosmic expansion and cooled to just a few degrees above absolute zero, it still fills every direction of the sky. If our eyes could detect microwave radiation, the entire universe would glow faintly around us. The existence of this radiation was predicted long before it was discovered. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman calculated that if the universe had once been hot and dense, it should still contain a faint background glow left over from its early stages. For years, this prediction remained purely theoretical. Then, in 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Telephone Laboratories in New Jersey. They were trying to eliminate a persistent source of background noise that seemed to be coming from every direction in the sky. At first, they suspected equipment problems. They carefully examined the antenna. They checked the electronics. They even removed a pair of pigeons that had been nesting inside the instrument and cleaning up what they politely described as white dielectric material. But the noise remained. Eventually they realized that the signal was not coming from their equipment at all. It was coming from the universe. What they had accidentally detected was the cosmic microwave background itself. The ancient radiation predicted decades earlier was quietly filling the sky, arriving at Earth from every direction with almost perfect uniformity. This discovery would later earn Penzias and Wilson the Nobel Prize in Physics, and it provided some of the strongest evidence that the Big Bang model of the universe was correct. Yet even though the cosmic microwave background appears almost perfectly smooth, it contains tiny variations in temperature. These differences are incredibly small. In most regions of the sky, the temperature varies by only about 1 part in 100,000. But these minute fluctuations carry profound meaning. They reveal that the early universe was not completely uniform. There were very slight differences in density from place to place. Some regions contained just a little more matter than average. Others contained slightly less. At first glance, these tiny variations might seem insignificant, but gravity is patient. Where matter is slightly denser, gravity pulls more strongly. Over time, these regions begin attracting additional gas and dark matter from their surroundings. The differences grow slowly larger. Like gentle ripples spreading across the surface of a pond, these subtle variations began shaping the structure of the entire cosmos. In fact, the entire large-scale architecture of the universe can be traced back to these tiny fluctuations visible in the cosmic microwave background. Every galaxy, every star, every planet, even the atoms that make up your body. All of them ultimately emerge from these faint irregularities in the early universe. But during the time immediately after recombination, none of that structure had fully formed yet. The universe had become transparent, but it remained almost completely dark. There were no stars producing visible light, no galaxies clustering together, no brilliant explosions lighting up the void. Instead, space was filled mostly with neutral hydrogen gas and helium drifting slowly through an expanding universe. And yet, beneath this calm and quiet surface, the forces that would eventually transform the cosmos were already at work. Gravity was gently gathering matter together. Dark matter, an invisible form of matter that does not interact with light, had already begun forming enormous structures that would act as gravitational scaffolding for future galaxies. Within these invisible frameworks, ordinary matter would eventually accumulate, cooling and collapsing into dense clouds of gas. Those clouds would give birth to the first stars, but that moment was still far in the future. For millions of years after recombination, the universe remained in a long twilight state. The ancient glow of the cosmic microwave background slowly faded as the universe expanded and cooled. At the same time, the first seeds of cosmic structure continued to grow almost imperceptibly. It was a universe that seemed almost empty, almost silent. But hidden within that quiet darkness were the beginnings of everything that would come later. The galaxies that would one day fill the cosmos. The stars that would forge the elements needed for planets. And eventually, the long chain of cosmic events that would lead to life itself. The universe, in its earliest transparent form, looked calm and simple, yet within its faint ripples and drifting atoms lay the entire blueprint of the future. Even though the early universe eventually slipped into darkness, it never lost the memory of its beginnings. That memory still surrounds us today. It exists as a faint glow that fills every direction in space, quietly arriving from the farthest reaches of the observable universe. This glow is so uniform and subtle that for most of human history, we had no idea it was there at all. Yet it carries within it a detailed record of conditions that existed when the universe was only a few 100,000 years old. This ancient radiation is known as the cosmic microwave background. If the night sky were sensitive to microwave wavelengths instead of visible light, we would see it everywhere. The entire sky would appear softly illuminated by a gentle background haze, almost perfectly even in every direction. Today, this radiation has cooled to a temperature of about 2.7 degrees above absolute zero. That is only a few degrees warmer than the coldest temperature that physics allows. But it was not always so cold. When the cosmic microwave background was first released during the period known as recombination, the temperature of the universe was roughly 3,000 degrees above absolute zero. At that time, the radiation was bright and energetic, filling space with visible and infrared light. Over billions of years, however, the universe expanded. As space stretched, the wavelengths of that radiation stretched as well. Light that once glowed in visible colors gradually shifted into longer wavelengths, eventually becoming microwave radiation. The process is a direct consequence of cosmic expansion. As the fabric of space grows larger, the light traveling through it is stretched along with it. The result is that radiation slowly loses energy and becomes colder. The cosmic microwave background is therefore both ancient and extremely distant. The photons we detect today began their journey nearly 14 billion years ago, shortly after the universe first became transparent. For cosmologists, this radiation is an extraordinary treasure. It provides the earliest observable image of the universe. In a very real sense, it is a photograph of the cosmos when it was only 380,000 years old. At first glance, that photograph looks remarkably smooth. If you map the temperature of the cosmic microwave background across the sky, nearly every region has almost exactly the same value, but not perfectly. When astronomers began measuring the background radiation with increasing precision, they discovered extremely small variations in temperature. These differences are tiny. In most places, the temperature changes by only about 1 part in 100,000. To picture how small that is, imagine measuring the height of Mount Everest and finding variations no greater than a few centimeters across its entire summit. Yet those tiny differences are enormously important. They reveal that the early universe contained small fluctuations in density. Some regions contained slightly more matter than average, others contained slightly less. Over time, gravity would amplify these differences, slowly turning them into the enormous structures we see today. Detecting those faint patterns required remarkable technological effort. One of the earliest breakthroughs came from a spacecraft called the Cosmic Background Explorer, often abbreviated as COBE. This satellite was launched by the National Aeronautics and Space Administration in 1989. COBE carried sensitive instruments designed to measure the temperature of the cosmic microwave background across the sky. In 1992, the mission announced one of the most important discoveries in modern cosmology. For the first time, scientists detected the tiny temperature fluctuations in the cosmic microwave background. The discovery confirmed that the early universe was not perfectly smooth. Instead, it contained the subtle irregularities required for galaxies and stars to form. George Smoot and John Mather, two of the scientists leading the COBE mission, later received the Nobel Prize in Physics for this work. Later missions improved the precision dramatically. The Wilkinson Microwave Anisotropy Probe, usually called WMAP, was launched in 2001. Over the following years, it produced detailed maps of the cosmic microwave background, measuring temperature variations across the entire sky with remarkable accuracy. Then came the Planck satellite, launched by the European Space Agency in 2009. Planck carried even more sensitive detectors and produced the most detailed map of the cosmic microwave background ever created. These observations revealed patterns that trace the earliest seeds of cosmic structure. Within the faint fluctuations of the background radiation, astronomers could see the imprint of acoustic waves that once rippled through the hot plasma of the early universe. They could measure the proportions of ordinary matter, and dark energy. They could estimate the age of the universe with extraordinary precision. All of that information was encoded in subtle temperature differences, only a few millionths of a degree wide. Understanding why those patterns look the way they do required careful theoretical work. One important concept was developed by the astrophysicist Joseph Silk in the late 1960s. Silk studied how photons and matter interacted in the dense plasma that filled the early universe. Before recombination, photons scattered constantly off free electrons, performing what physicists describe as a random walk through the plasma. Because of this scattering, radiation could slowly diffuse from hotter regions into cooler ones. This process gradually erased smaller fluctuations in density. The phenomenon is now known as silk damping. In simple terms, silk damping smoothed out the tiniest irregularities in the early universe, leaving behind only the larger patterns that we can observe today in the cosmic microwave background. Without this effect, the temperature map of the universe might look far more chaotic. Another important discovery connects the ancient radiation of the cosmic microwave background with structures that formed billions of years later. This phenomenon is called the Sunyaev-Zeldovich effect, named after the Russian astrophysicists Rashid Sunyaev and Yakov Zeldovich. When cosmic microwave background photons pass through a galaxy cluster, they encounter extremely hot electrons inside the cluster's gas. These energetic electrons can transfer energy to the passing photons. As a result, the photons leave the cluster slightly more energetic than before. This interaction subtly distorts the cosmic microwave background in regions where large galaxy clusters exist. By measuring these distortions, astronomers can detect clusters of galaxies even when they are extremely distant. The Sunyaev-Zeldovich effect therefore creates a bridge between the ancient universe and the large-scale structures that developed much later. It reminds us that the cosmic microwave background is not simply a relic frozen in time. It continues interacting with the universe as it travels across space. When scientists map the cosmic microwave background today, they are essentially studying the earliest blueprint of cosmic architecture. Those tiny temperature fluctuations mark the locations where matter was just slightly denser than average. Over millions and billions of years, gravity pulled additional material into those regions. Some of them grew into enormous galaxy clusters containing thousands of galaxies. Others became the birthplaces of individual galaxies like our own Milky Way, and in many cases the faint seeds visible in the cosmic microwave background eventually produced the stars that would illuminate the universe. In that sense, the cosmic microwave background is more than an ancient glow. It is a map of possibility. Every small ripple in that radiation represents a place where gravity would begin shaping the universe into something more complex. Every faint variation marks the earliest trace of a structure that might later grow into galaxies, stars, and planets. Looking at those patterns is like examining the blueprint of a vast cosmic city before any of the buildings have been constructed. At the time the radiation was released, the universe still appeared calm and nearly uniform. But hidden within that delicate pattern was the entire future of the cosmos. Those faint temperature variations in the cosmic microwave background raise an intriguing question. Why were there fluctuations in the first place? If the universe began in an extremely hot and dense state, and if matter and radiation were once thoroughly mixed together, one might expect the early cosmos to have been almost perfectly uniform. Yet observations show that this was not quite the case. Tiny irregularities were already present long before galaxies and stars existed. To understand where those irregularities came from, cosmologists look even further back in time, to an era that occurred far earlier than the release of the cosmic microwave background. This earlier event is known as cosmic inflation. Inflation is a theoretical framework proposed in 1980 by the physicist Alan Guth. Guth was trying to solve several puzzling problems in cosmology, including why the observable universe appears so remarkably uniform and why space seems almost perfectly flat on the larger scales. His solution suggested that the very young universe experienced an extraordinary burst of expansion. During this brief interval, space itself expanded at an astonishing rate. Regions that were once extremely close together were suddenly stretched far apart. Distances that had once been microscopic could become astronomically large in an incredibly short period of time. The timescale involved is almost difficult to comprehend. Inflation is thought to have occurred when the universe was far less than a second old. In fact, the entire episode may have lasted only a tiny fraction of a second, perhaps something like 1/10 trillionth of a trillionth of a trillionth of a second. Yet during that minuscule moment, the size of the universe may have increased by an enormous factor. Some calculations suggest that space expanded by at least 100 trillion times its original scale. The key idea is that inflation did not involve galaxies flying apart through space. Instead, the expansion occurred in the fabric of space itself. Distances between points grew rapidly, carrying matter and radiation along for the ride. In many ways, inflation smoothed out the young universe. Regions that had once been extremely dense and chaotic were stretched so dramatically that the observable universe ended up appearing remarkably uniform. But inflation did something else as well. While it smoothed out the cosmos on large scales, it also amplified the tiniest possible irregularities. At the smallest scales known to physics, nature is governed by the rules of quantum mechanics. According to quantum theory, energy and fields can never remain perfectly still. Even in a vacuum, small fluctuations constantly appear and disappear. These are called quantum fluctuations. Under ordinary circumstances, quantum fluctuations are unimaginably small and vanish almost instantly. They occur on scales far smaller than atoms and exist for extremely short periods of time. But during inflation, something unusual happened. Because space was expanding so rapidly, these microscopic fluctuations were stretched outward along with the fabric of the universe itself. Tiny variations that once existed on subatomic scales were enlarged to astronomical sizes. What began as fleeting quantum ripples eventually became density variations spread across enormous regions of space. The theoretical groundwork for this idea was developed in the early 1980s by physicists Vyacheslav Mukhanov and Gennady Chibisov. Their calculations showed that quantum fluctuations during inflation would naturally produce the kinds of density variations that cosmologists observe today in the cosmic microwave background. These fluctuations would not be random in just any pattern. Instead, inflation predicts a very specific distribution known as scale-invariant density fluctuations. The phrase scale-invariant means that fluctuations appear with roughly the same strength across many different sizes. Whether you examine a region of space spanning hundreds of millions of light-years or one only a few million light-years wide, the relative differences in density remain surprisingly similar. This pattern turns out to match observations remarkably well. When satellites such as WMAP and the Planck Observatory mapped the cosmic microwave background, they found that its fluctuations follow exactly the kind of statistical pattern predicted by inflationary theory. The early universe, it seems, truly did contain tiny irregularities distributed across many different scales. These irregularities were incredibly small at first. In the early universe, density differences were only about 1 part in 100,000. That means that in a region containing 100,000 particles, one region might have contained just one additional particle compared to another. Yet gravity does not require large differences to begin working. Even the slightest excess of matter creates a slightly stronger gravitational pull. Over time, that extra pull attracts more material, gradually increasing the density further. What began as a microscopic imbalance slowly becomes a growing clump of matter. Given enough time, those clumps evolve into the vast cosmic structures we see today. This process eventually produces enormous filaments of galaxies stretching across hundreds of millions of light years. It creates galaxy clusters containing thousands of galaxies. It shapes the large-scale structure of the universe, sometimes described as the cosmic web. All of that complexity began with the quantum fluctuation stretched by inflation. Testing the theory of inflation is not easy. The event occurred extremely early in cosmic history, long before the universe became transparent. However, inflation makes several predictions that astronomers can attempt to measure. One particularly exciting possibility involves primordial gravitational waves. Gravitational waves are ripples in spacetime predicted by Albert Einstein's theory of general relativity. In 2015, scientists working with the Laser Interferometer Gravitational Wave Observatory, often called LIGO, detected gravitational waves produced by merging black holes. But inflation predicts something even more ancient. If inflation occurred, it may have generated gravitational waves that spread throughout the early universe. These waves would leave subtle signatures in the polarization patterns of the cosmic microwave background. Detecting those patterns would provide strong evidence that inflation really happened. Several experiments are searching for this signal. One of the best known is the background imaging of cosmic extragalactic polarization experiment, usually shortened to BICEP. The BICEP telescopes are located at the South Pole, where the cold, dry atmosphere allows extremely sensitive observations of microwave radiation. Researchers working on these experiments carefully study the polarization of the cosmic microwave background, searching for the faint imprint of primordial gravitational waves. The challenge is enormous. The signal, if it exists, is incredibly subtle and can easily be confused with foreground radiation from dust within our own galaxy. Even so, the search continues, and each new generation of instruments becomes more precise. Whether or not inflation is eventually confirmed in every detail, the idea has already reshaped how cosmologists think about the origin of cosmic structure. It provides a compelling explanation for why the universe appears both remarkably uniform and subtly patterned at the same time. Without those primordial fluctuations, the universe would have remained almost perfectly smooth. Gas would never have gathered into dense clouds. Stars would never have formed. Galaxies would never have assembled. Instead, the cosmos might have remained a vast, thin ocean of hydrogen and helium, drifting endlessly through expanding space. But thanks to those tiny quantum ripples, the universe inherited a kind of cosmic blueprint. Over billions of years, gravity followed that blueprint carefully. The faint fluctuations imprinted during inflation became the starting points for every galaxy, every star, and every planet that would eventually appear. Even the Milky Way itself can trace its origins back to one of those subtle ripples in the early universe. A tiny variation in density, stretched across cosmic space, patiently waiting for gravity to begin its work. The early universe did not simply become quiet by accident. Its transformation from a hot, dense plasma into a calm, transparent sea of atoms followed clear physical laws. Those laws come from thermodynamics, the branch of physics that describes how energy, heat, and matter behave as systems expand, cool, and change over time. One of the key figures who studied these principles in a cosmological context was the American physicist Richard Tolman. In the early 20th century, Tolman explored how thermodynamics works within Einstein's theory of general relativity, where space itself can expand or contract. Tolman recognized something profound. If the universe is expanding, then its temperature cannot remain constant. Expansion changes how energy is distributed throughout space, and as space stretches, the energy density of radiation and matter must gradually decline. In simple terms, when the universe expands, it cools. This cooling process is not mysterious. It follows a straightforward physical principle called adiabatic expansion. Adiabatic expansion occurs when a gas expands without gaining additional heat from outside sources. As the gas spreads out, the particles inside it lose energy, and the overall temperature falls. A familiar example appears when compressed air escapes from a pressurized container. As the gas expands into a larger space, it cools noticeably, The same principle applies on cosmic scales. In the early universe, space itself expanded. As it did, both radiation and matter became less dense. Photons stretched to longer wavelengths, losing energy, while particles drifted farther apart. The result was a steady, predictable cooling of the entire cosmos. To appreciate how dramatic this cooling was, it helps to imagine the temperature history of the universe. Shortly after the Big Bang, temperatures were extraordinarily high, reaching trillions of degrees. Under those conditions, atoms could not exist. Matter existed only as a dense soup of fundamental particles such as quarks, electrons, and neutrinos. As the universe expanded and cooled, protons and neutrons eventually formed. A few minutes later, nuclear reactions produced the first atomic nuclei. These reactions are known as Big Bang nucleosynthesis. During this brief period, the universe produced the nuclei of hydrogen, helium, and tiny amounts of lithium. The proportions were remarkably specific. Roughly 75% of ordinary matter formed as hydrogen nuclei, which are simply single protons, while about 25% became helium nuclei containing 2 protons and 2 neutrons. These ratios have been measured in ancient gas clouds and match theoretical predictions with impressive accuracy. But at this stage, the universe was still far too hot for electrons to attach themselves to these nuclei. Instead, matter remained in the form of a plasma. A plasma is a state of matter in which electrons are not bound to atoms but move freely among charged particles. In this environment, light interacts constantly with matter. Photons scatter off electrons repeatedly, preventing radiation from traveling freely. For hundreds of thousands of years, the universe remained in this glowing plasma state. During that time, cooling continued steadily as the cosmos expanded. Eventually, the temperature dropped to roughly 3,000 degrees above absolute zero. At that point, conditions became cool enough for electrons to combine with atomic nuclei. This process created the first stable atoms. The event is known as recombination, although the name is somewhat misleading. In truth, electrons and nuclei were joining together for the first time, not recombining after an earlier separation. Despite the imperfect terminology, the name has remained in use throughout cosmology. Understanding recombination in detail required careful theoretical work. In 1970, cosmologist James Peebles and Yu developed one of the earliest detailed calculations describing how hydrogen atoms formed in the cooling universe. Their work showed that recombination was not an instantaneous event. Instead, it unfolded gradually as temperatures fell and more electrons became bound to protons. In later decades, scientists such as Jens Schluber refined these calculations further. Using modern computational methods, researchers examined subtle processes that occur during recombination, including the exact ways photons interact with hydrogen atoms and how energy transitions affect the rate at which atoms form. These refinements improved our ability to interpret the cosmic microwave background with extraordinary precision. When recombination finally progressed far enough, the universe underwent a dramatic transformation. Free electrons largely disappeared as they became bound inside neutral atoms. With far fewer charged particles available to scatter photons, radiation could travel freely through space. Light that had once been trapped in a dense fog of plasma suddenly escaped. That ancient light continues traveling through the universe today as the cosmic microwave background. Meanwhile, matter itself had settled into a much calmer state. The vast majority of ordinary matter now existed as neutral hydrogen atoms. Helium atoms formed as well, though in smaller numbers. Hydrogen dominated because it required only 1 proton and 1 electron to form. This simple element would later become the primary fuel for stars. At this stage, however, the universe contained almost nothing except hydrogen, helium, dark matter, and radiation. The temperature continued to fall as expansion progressed. Adiabatic cooling steadily reduced the energy of particles and radiation alike. Gas became colder and thinner as space expanded further. Over time, the universe entered a quiet phase in which no major sources of light existed. This period is often called the Cosmic Dark Ages. The phrase may sound dramatic, but in practice the era was simply one of calm simplicity. The universe contained atoms drifting through an ever-expanding volume of space. The cosmic microwave background gradually faded as its photons stretched to longer wavelengths. Gravity was present, of course, but its effects unfolded slowly. The tiny density fluctuations inherited from earlier cosmic processes were still extremely small. Gas clouds had not yet collapsed into stars. Galaxies had not yet formed. From the perspective of visible light, the universe had grown dark. Yet this darkness did not mean that nothing was happening. Within the expanding sea of hydrogen and helium, gravity was quietly beginning its patient work. Regions that contained slightly more matter than average began attracting additional material. The process was slow and subtle, unfolding across millions of years. But the calm conditions created by cosmic cooling made this gradual evolution possible. If the universe had remained extremely hot, particles would have moved too quickly for gravity to gather them together. The cooling caused by expansion allowed matter to settle into structures. In that sense, the Dark Ages were not merely an empty pause in cosmic history. They were a necessary preparation. The universe had cooled, the plasma had faded into atoms, and space had become transparent. The stage was now set for gravity to begin shaping the first cosmic structures. And within those structures, eventually the first stars would ignite. As the universe cooled and entered its long quiet period, gravity slowly began shaping matter into the first structures. But there was an important complication that astronomers would only discover much later. The matter we can see, the atoms that make up stars, planets, gas clouds, and people, appears to represent only a small fraction of the total matter in the universe. Most of the universe's mass is hidden. This mysterious component is known as dark matter. The name is straightforward but somewhat misleading. Dark matter is not simply ordinary matter that happens to be dim or difficult to see. Instead, it appears to be a completely different form of matter that does not interact with light at all. It does not emit radiation. It does not absorb light. It does not reflect anything that telescopes can detect. And yet its gravitational influence is unmistakable. The idea first emerged in the 1930s through the work of the Swiss astronomer Fritz Zwicky. Zwicky was studying the Coma Cluster, a massive group of galaxies located hundreds of millions of light-years away. By measuring how fast the galaxies in the cluster were moving, Zwicky calculated how much mass the cluster must contain in order to hold those galaxies together through gravity. The result was startling. The galaxies were moving far too quickly to remain gravitationally bound, if only the visible stars and gas were providing the gravitational pull. According to Zwicky's calculations, the cluster needed far more mass than astronomers could see. He concluded that the cluster must contain a large amount of unseen matter. Zwicky referred to this invisible material as Dunkelmaterie, the German phrase for dark matter. At the time, the idea did not immediately transform astronomy. Many researchers suspected that the discrepancy might be explained by faint stars, cold gas, or observational uncertainties. But over the following decades, additional evidence slowly accumulated. One of the most compelling discoveries came from the work of the American astronomer Vera Rubin in the 1970s. Rubin and her colleague Kent Ford studied how stars move within spiral galaxies. In a typical galaxy, stars orbit around the central region much like planets orbit around a star. According to Newtonian gravity, objects farther from the center should move more slowly, because the gravitational pull becomes weaker with distance. This expectation can be expressed by a simple relationship between gravitational force and orbital motion. In classical mechanics, orbital velocity is related to mass and distance through the equation. Velocity squared equals the gravitational constant multiplied by mass divided by radius. If most of a galaxy's mass were concentrated near its center, stars in the outer regions should move noticeably more slowly. But Rubin's observations revealed something quite different. When she measured the rotation speeds of stars in spiral galaxies, she found that the outer stars were moving almost as fast as the inner ones. Instead of declining with distance, the rotation curves remained nearly flat. The only way to explain this behavior was to assume that galaxies contain vast halos of unseen matter, extending far beyond their visible disks. These halos must contain far more mass than the stars themselves. Today, astronomers believe that dark matter outweighs ordinary matter by roughly a factor of 5. In other words, about 85% of the matter in the universe appears to be dark matter. Ordinary atoms make up only a small minority of the cosmic mass budget. This realization fundamentally changed our understanding of cosmic structure. Dark matter does not interact with light, but it does respond to gravity. In the early universe, it began collapsing into structures long before ordinary gas could do the same. Because dark matter particles rarely collide or interact with each other, they can move freely through space while still responding to gravitational attraction. Over time, regions containing slightly more dark matter grew denser. These dense regions formed enormous structures known as dark matter halos. Dark matter halos act like gravitational containers. They create deep wells of gravity that pull ordinary matter inward. Hydrogen and helium gas slowly falls into these halos, eventually forming stars and galaxies. Without dark matter halos, galaxies might never have formed at all. The modern framework describing this process is known as the lambda cold dark matter model, often called the lambda CDM model. In this name, the Greek letter lambda represents dark energy, the mysterious force causing the expansion of the universe to accelerate. The phrase cold dark matter refers to dark matter particles that move relatively slowly compared with the speed of light. This model describes a universe composed primarily of dark energy and dark matter, with ordinary matter representing only a small fraction of the total. Within this framework, dark matter forms the large-scale skeleton of the universe. Ordinary matter follows this invisible structure, gathering in the densest regions where galaxies eventually form. Much of our understanding of how dark matter halos behave comes from sophisticated computer simulations. In the 1990s, astrophysicists Carlos Frenk, Simon White, and Julio Navarro developed models describing how dark matter distributes itself inside halos. Their work led to a mathematical description known as the Navarro-Frenk-White profile, which predicts how density changes from the center of a halo to its outer edges. According to this model, dark matter halos have dense central regions surrounded by more diffuse outer layers extending across enormous distances. Computer simulations using billions of virtual particles have shown how these halos grow over time, merging with one another and forming a vast interconnected structure known as the cosmic web. In these simulations, the universe resembles a network of filaments stretching across space. At the intersections of these filaments, large concentrations of dark matter form galaxy clusters and superclusters. Galaxies like the Milky Way occupy smaller halos embedded within this enormous cosmic network. Despite its importance, dark matter remains one of the most mysterious substances in modern physics. Scientists still do not know exactly what it is made of. Many experiments have searched for dark matter particles interacting with detectors on Earth, but so far the results have been inconclusive. Particle physicists have proposed several possible candidates, each with different theoretical motivations. One intriguing possibility involves hypothetical particles known as axions. The axion concept was introduced in the 1970s by physicists Roberto Peccei and Helen Quinn, while studying a subtle symmetry problem in quantum chromodynamics, the theory describing the strong nuclear force. Axions were not originally proposed as dark matter particles. However, later research suggested that if axions exist, they could be produced in enormous numbers during the early universe. Because they would interact extremely weakly with ordinary matter and radiation, they could persist today as a vast invisible population of particles filling the cosmos. Several experiments are now searching for axions using highly sensitive detectors that attempt to convert axions into detectable microwave signals within strong magnetic fields. Whether axions or some other particle ultimately prove to be the correct explanation remains uncertain. But regardless of its precise nature, the gravitational influence of dark matter is unmistakable. During the cosmic dark ages, long before the first stars ignited, dark matter had already begun building the hidden architecture of the universe. Its invisible halos provided the gravitational scaffolding upon which galaxies would later assemble. While ordinary atoms drifted quietly through expanding space, dark matter was already shaping the future structure of the cosmos. In that sense, the first galaxies were not created from nothing. They were built within an unseen framework that had been forming for millions of years, quietly guiding the evolution of matter across the vast darkness of the early universe. Once the universe had cooled and settled into its long, quiet phase, the stage was set for one of the most patient forces in nature to begin shaping the cosmos. That force was gravity. Gravity is often described as weak compared with the other fundamental forces of physics. The electromagnetic force, for example, is vastly stronger at small scales, yet gravity has one enormous advantage: it never cancels out. Electric charges can repel or attract each other depending on their sign, but gravity always pulls in the same direction. Every particle with mass attracts every other particle with mass. Over short periods of time, this attraction may appear negligible, but given millions or billions of years, gravity becomes the architect of the universe. In the early universe, gravity began its work by acting on the tiny density fluctuations that already existed. As we have seen, these fluctuations were incredibly small. Some regions contained only slightly more matter than their surroundings, but even a slight excess of mass creates a slightly stronger gravitational pull. Where matter was just a little denser, gravity tugged more strongly on nearby gas and dark matter. That additional matter slowly drifted toward the denser region, increasing its mass further. The process feeds on itself. As the region grows denser, its gravitational pull strengthens. That stronger pull attracts even more material, which increases the density further still. This mechanism is known as gravitational instability. It is one of the fundamental processes responsible for building cosmic structure. Starting from tiny variations in density, gravitational instability gradually amplifies those differences over time. The concept can be understood with a simple mental picture. Imagine a shallow landscape where some areas dip slightly lower than others. If water begins flowing across that surface, it will slowly gather in the lowest spots. As water accumulates there, the depressions deepen, attracting even more water. The early universe behaved in a somewhat similar way, except the role of flowing water was played by matter responding to gravity. Understanding how this process unfolds across cosmic scales required new mathematical tools. One important step was developed by the Soviet physicist Yakov Zeldovich. Zeldovich introduced a method now known as the Zeldovich approximation, which describes how matter moves under gravity during the early stages of structure formation. In this approximation, particles of matter begin moving along trajectories determined by the gravitational potential created by density fluctuations. At first, the movements are small and orderly. Matter drifts slowly toward regions of higher density, forming sheet-like structures and elongated filaments. These structures gradually grow thicker as more material accumulates. The Zeldovich approximation works particularly well during the early stages of gravitational collapse, when the density contrasts are still relatively small. As time passes, however, gravity drives the system into increasingly complex behavior. Regions of higher density eventually collapse more dramatically, creating compact structures that can trap matter gravitationally. Predicting exactly how many such structures would form across the universe became another major challenge for cosmologists. In the 1970s, physicists William Press and Paul Schechter developed a statistical framework to address this problem. Their work introduced what is now known as the Press-Schechter formalism. The central idea was to use probability theory to estimate how many regions of space would eventually collapse into gravitationally bound objects. Press and Schechter began by examining the distribution of density fluctuations in the early universe. Because those fluctuations were extremely small, they could be described using statistical methods similar to those used in fields such as statistical mechanics. From this starting point, they calculated how likely it was for regions of different sizes to exceed the critical density needed for gravitational collapse. In simple terms, the Press-Schechter formalism predicts how many structures of various masses should form as the universe evolves. It estimates the number of small halos, medium-sized halos, and extremely massive halos that will appear over cosmic time. Although later refinements have improved the details, the Press-Schechter approach remains one of the foundational tools for understanding cosmic structure formation. Of course, mathematical approximations alone cannot capture the full complexity of the universe. As computers became more powerful during the late 20th century, cosmologists began performing large-scale simulations that followed the motion of millions and eventually billions of particles under the influence of gravity. One researcher who made significant contributions to this field was Ed Bertschinger, a cosmologist who studied how matter collapses and forms structures under gravitational forces. Using numerical simulations, scientists like Bertschinger were able to watch virtual universes evolve over billions of years. These simulations begin with conditions similar to those measured in the cosmic microwave background. Tiny density fluctuations are distributed across a large region of space. Then gravity is allowed to act. As time progresses, the particles representing matter begin clustering together. Small clumps merge into larger ones. Filaments stretch between growing structures. Vast voids appear where matter has been drawn away. The result is the formation of a complex network known as the cosmic web. This web is composed of enormous filaments of matter connecting dense clusters of galaxies. Between these filaments lie vast regions with very little matter, sometimes spanning hundreds of millions of light-years. The cosmic web is one of the most striking patterns in the universe. Large galaxy surveys such as the Sloan Digital Sky Survey have mapped the positions of millions of galaxies and confirmed that the real universe exhibits the same web-like structure predicted by simulations. Galaxies are not distributed randomly through space. Instead, they trace out an intricate network shaped by the slow pull of gravity over billions of years. What is remarkable is that all of this structure began from fluctuations so small that they were barely detectable in the early universe. Gravity did not need dramatic differences to begin its work, it only required time. During the cosmic dark ages, this process unfolded gradually. Dark matter began collapsing into halos while ordinary matter slowly followed, drifting into the same gravitational wells. The growth was slow at first. Because the density contrasts were tiny, the gravitational forces involved were weak. It took millions of years for noticeable changes to occur. But once structures began forming, the process accelerated. Larger halos attracted more matter, which allowed them to grow even larger. Eventually, these halos became the birthplaces of the first stars. Looking back across cosmic history, it is astonishing how much complexity emerged from such modest beginnings. The galaxies that fill the observable universe, the clusters containing thousands of galaxies, and the immense filaments stretching across hundreds of millions of light-years all began as faint ripples in the density of the early universe. Those ripples were amplified by gravity, slowly but relentlessly. And through that steady amplification, gravity transformed a nearly uniform universe into the richly structured cosmos we see today. As gravity continued its slow and steady work across the expanding universe, the invisible matter we call dark matter began gathering into distinct structures. These structures are known as dark matter halos. A dark matter halo is a region where dark matter has collapsed under its own gravity to form a dense concentration surrounded by a more diffuse outer envelope. Although the word halo might sound delicate or decorative, in cosmology it describes an enormous gravitational structure that can span hundreds of thousands of light-years. Galaxies form inside these halos. In fact, the visible parts of galaxies, the stars, gas, and dust we can observe with telescopes, occupy only the innermost regions of much larger halos made primarily of dark matter. The halo itself is invisible, but its gravitational influence shapes everything that happens inside it. Understanding how these halos formed requires returning to the early universe, when density fluctuations were still very small. Dark matter responded to gravity more quickly than ordinary gas because it does not interact strongly with radiation. Ordinary matter, especially in the early universe, was coupled to radiation through electromagnetic interactions. Photons scattered constantly off charged particles, preventing gas from collapsing easily. Dark matter had no such limitation. Because it interacts primarily through gravity, dark matter began clustering earlier and more efficiently. As the universe expanded and cooled, regions with slightly higher dark matter density started pulling in surrounding material. Gradually, these regions collapsed into gravitationally bound halos. At first, the halos were relatively small, but as time passed, they continued growing by pulling in additional matter from their surroundings. Halos also merged with one another. When two halos drifted close together, their mutual gravitational attraction often caused them to combine into a single, larger structure. Over cosmic time, countless mergers gradually produced halos of increasing mass. This process is known as hierarchical structure formation. The word hierarchical simply means that small structures form first, and larger structures grow by combining those smaller pieces. The early universe followed this pattern remarkably well. Tiny dark matter halos appeared first. These halos merged into somewhat larger halos. Those larger halos eventually merged into the enormous structures that host modern galaxies and galaxy clusters. Much of what we know about this process comes from large-scale computer simulations. One of the most influential examples is the Millennium Simulation, a project carried out by an international team of researchers led in part by astrophysicist Volker Springel at the Max Planck Institute for Astrophysics. The Millennium Simulation tracked the motion of more than 10 billion particles representing dark matter across a region of space several billion light-years wide. By allowing gravity to act on those particles over cosmic time, scientists could watch a virtual universe evolve from early density fluctuations into the intricate cosmic web observed today. The results were striking. Filaments of dark matter stretched across enormous distances, forming a vast network that connected clusters and groups of galaxies. Dense knots of matter appeared at the intersections of these filaments, while immense voids formed in regions where matter had been pulled away. The simulation revealed how dark matter halos grow, merge, and organize themselves into larger structures. Most importantly, it showed that galaxies form naturally within these halos. Ordinary gas falls into the gravitational wells created by dark matter, gradually cooling and settling toward the center. Over time, this gas becomes dense enough to form stars. But long before galaxies like the Milky Way existed, the universe contained far smaller dark matter structures. These early halos are known as mini-halos. Mini-halos were among the first gravitationally bound objects to appear in the universe. Their masses were relatively modest by cosmic standards, often containing roughly 100,000 to 1 million times the mass of the Sun. That may sound enormous, but compared with modern galaxy halos, which can contain trillions of solar masses, mini-halos were quite small. Despite their modest size, mini-halos played a crucial role in cosmic history. They provided the first gravitational shelters where ordinary matter could begin accumulating in significant amounts. Hydrogen and helium gas drifting through the early universe slowly fell into these dark matter wells. As gas descended into a halo, gravity caused it to compress and heat slightly. Over time, the gas settled toward the central regions of the halo, but this accumulation was not instantaneous. Gas does not simply fall inward without resistance. Pressure forces, thermal energy, and subtle interactions between particles all influence how the gas behaves. In the earliest halos, gas needed a way to cool before it could collapse further. Cooling allows particles to lose energy, making it easier for gravity to pull them closer together. Without an efficient cooling mechanism, gas would remain too warm and diffuse to form dense structures. In the early universe, one of the most important cooling agents was a simple molecule made from hydrogen atoms. This molecule is known as molecular hydrogen. Even though it formed only in small amounts, molecular hydrogen could radiate away energy as it changed between different rotational and vibrational states. This allowed gas inside mini-halos to cool enough for gravity to compress it further. As cooling continued, the central regions of some halos eventually became dense enough to begin forming the first stars. But before those stars ignited, the halos themselves continued evolving. Halos did not remain isolated for long. Because the cosmic web constantly shifted and flowed under gravity, halos drifted through space and frequently encountered one another. When two halos approached closely enough, they often merged. The merging process could be gentle or violent depending on the relative masses and velocities involved. Smaller halos might simply be absorbed by larger ones, contributing their matter to the growing structure. Over time, repeated mergers produced halos of increasing mass. Some eventually grew large enough to host entire galaxies. Yet in the earlier stages of cosmic history, the universe was filled mostly with these smaller halos scattered throughout the cosmic web. Each halo represented a region where gravity had gained a foothold. Each one gathered gas slowly from the surrounding universe, and within some of those halos the conditions were gradually becoming suitable for a remarkable event, the birth of the very first stars. Although these early halos were invisible to our eyes and to most telescopes, they formed the essential foundation for everything that followed. Without dark matter halos, gas would have remained spread thinly throughout space. Gravity alone would not have been strong enough to gather matter into dense clouds capable of igniting nuclear fusion. But with halos acting as gravitational anchors, the universe began assembling the structures that would eventually produce light. In that sense, the first stars did not appear randomly across the cosmos. They emerged inside the quiet gravitational shelters created by dark matter, within halos that had been forming patiently during the long, dark ages of the universe. Long before the first star ever ignited, the universe was filled with an extremely simple mixture of ingredients. There were no heavy elements such as carbon, oxygen, silicon, or iron. No complex molecules drifting through interstellar space. None of the rich chemical diversity that fills modern galaxies. Instead, the early cosmos was composed almost entirely of just two elements, hydrogen and helium. These elements were produced during the first few minutes after the Big Bang through a process known as Big Bang nucleosynthesis. During that brief period, temperatures were high enough for nuclear reactions to fuse protons and neutrons together, into light atomic nuclei. The results of those reactions were remarkably consistent. About 3/4 of the ordinary matter in the universe emerged as hydrogen. Most of the remaining quarter became helium. Only tiny traces of other elements were produced, including small amounts of lithium and beryllium. After those early minutes, the universe expanded and cooled too rapidly for further nuclear reactions to continue. The chemical composition of the cosmos remained almost completely unchanged for hundreds of millions of years. This means that during the cosmic dark ages, the universe contained almost nothing except hydrogen atoms, helium atoms, dark matter, and radiation left over from earlier epochs. At first glance, this might seem like an unpromising recipe for building stars. Modern star-forming regions inside galaxies contain dust grains, complex molecules, and a wide range of heavier elements that help gas cool efficiently. In contrast, the early universe lacked almost all of those ingredients, and yet stars eventually formed. The key to this transformation lies in a surprisingly simple piece of cosmic chemistry. Although the early universe contained mostly individual hydrogen atoms, under the right conditions those atoms could occasionally combine to form a molecule known as molecular hydrogen. Molecular hydrogen consists of 2 hydrogen atoms bound together. Today, it is the most abundant molecule in the universe and plays a central role in star-forming regions within galaxies. But forming this molecule in the early universe was not straightforward. Under ordinary circumstances, 2 hydrogen atoms cannot simply collide and stick together. When they attempt to form a molecule, the excess energy must be carried away somehow. Otherwise, the atoms will simply separate again. In modern galaxies, dust grains often help solve this problem. Hydrogen atoms can attach themselves to the surface of dust particles, where they meet other hydrogen atoms and combine into molecules. However, the early universe contained almost no dust. Instead, molecular hydrogen formed through a series of more subtle reactions involving charged particles. One important pathway begins when a hydrogen atom captures a free electron, forming a temporary ion known as a hydrogen-negative ion. This ion can then interact with another hydrogen atom, producing molecular hydrogen and releasing the extra electron. Although these reactions occurred only rarely, the vast scale of the universe meant that even rare events could gradually produce significant amounts of molecular hydrogen. Once molecular hydrogen existed, it played a crucial role in the evolution of primordial gas. The reason lies in how molecules interact with radiation. Molecules possess rotational and vibrational energy levels that allow them to emit radiation as they change between different states. When a molecule emits radiation, it carries energy away from the gas around it. This process allows the gas to cool. Cooling is essential for gravitational collapse. When gas is hot, particles move rapidly and create pressure that resists compression. Gravity must overcome that pressure in order to pull matter together into dense structures. But when gas cools, particle motions slow down, pressure decreases, and gravity gains the advantage. In the early universe, molecular hydrogen became the primary mechanism allowing gas clouds to lose energy and cool. This insight emerged through the work of several astrophysicists studying the formation of the first stars. Among them were researchers such as Tom Abel and Volker Bromm, who used detailed computer simulations to explore how primordial gas behaves inside early dark matter halos. Their simulations showed that even small amounts of molecular hydrogen could dramatically influence the fate of a gas cloud. When gas falls into a dark matter halo, gravitational compression heats the gas slightly. Without an efficient cooling process, that heat would prevent further collapse. But molecular hydrogen molecules can emit radiation at infrared wavelengths, allowing the gas to shed energy. As the gas cools, gravity pulls it inward more effectively. The density increases, making collisions between particles more frequent. These collisions can create additional molecular hydrogen, strengthening the cooling process. The cycle gradually intensifies. Gas becomes denser, cooling becomes more effective, gravity pulls even more strongly. Eventually, the central region of the cloud can collapse into a dense core. This process marks the beginning of star formation. In modern star-forming regions, many different molecules and dust grains contribute to cooling. But in the early universe, molecular hydrogen carried almost the entire burden of this task. Without it, the first stars might never have formed. The simplicity of primordial chemistry therefore played a surprisingly powerful role in shaping the universe. With only hydrogen, helium, and a few trace particles available, the cosmos still managed to create the conditions needed for gravitational collapse. Those early chemical reactions were slow and delicate, but they were sufficient. Within dark matter halos scattered across the young universe, gas clouds enriched with small amounts of molecular hydrogen began cooling and contracting. Over time, these clouds grew denser and more compact, and deep inside their collapsing cores, the universe was preparing to ignite its first stars. Inside the growing dark matter, halos scattered across the young universe, ordinary matter slowly began to gather. At first, this process unfolded almost imperceptibly. Hydrogen and helium gas drifting through space responded to the gravitational pull of dark matter. As gas moved through the expanding universe, regions containing dark matter halos created slightly deeper gravitational wells than their surroundings. These wells gently pulled nearby gas inward. The process was not dramatic. There were no violent explosions or sudden collapses. Instead, gas gradually drifted toward the centers of these halos over long stretches of time. As more matter accumulated, the central regions of halos became denser and warmer. Gravity was beginning to concentrate matter. But gathering gas was only the first step. For stars to form, the gas had to collapse into much denser structures. That collapse required cooling. When gas falls into a gravitational well, its motion converts gravitational energy into heat. As particles collide with one another, their kinetic energy increases and the temperature rises. Hot gas creates pressure that pushes outward, resisting further compression. If the gas cannot lose that heat, collapse will stop. This is where the chemistry of molecular hydrogen played its crucial role. As molecular hydrogen emitted radiation, it carried energy away from the gas cloud. That radiation escaped into space, allowing the cloud to cool. As the temperature dropped, the pressure inside the cloud weakened. Gravity could then pull the gas inward more effectively. Over time, this cycle gradually transformed diffuse gas into increasingly dense concentrations within the centers of dark matter halos. Understanding how this process unfolded required detailed theoretical work and powerful computer simulations. One of the earliest breakthroughs came from a group of astrophysicists including Tom Abel, Greg Bryan, and Michael Norman. In the late 1990s and early 2000s, they performed some of the first high-resolution simulations of primordial star formation. Their simulations followed the evolution of gas inside a small dark matter halo, under the influence of gravity, hydrodynamics, and chemical reactions involving molecular hydrogen. The results revealed something remarkable. Instead of collapsing smoothly into a single uniform structure, the gas developed a dense central core surrounded by a rotating envelope of material. As gravity continued pulling matter inward, the central region grew increasingly dense. Eventually, the simulations reached densities high enough that a protostar, the earliest stage of a star, would begin forming. These calculations provided the first detailed picture of how the very first stars might have emerged from primordial gas. Other researchers soon expanded upon this work. Astrophysicist Naoki Yoshida, working with collaborators in Japan and elsewhere, conducted further simulations exploring how early gas clouds behave inside dark matter halos. These studies examined how gas flows, turbulence, and chemical reactions influence the collapse of primordial clouds. One particularly interesting result emerged from these simulations. In modern star-forming regions inside galaxies, gas clouds often fragment into many smaller clumps. Each clump may eventually form a separate star, producing clusters of stars with a wide range of masses. But in the early universe, fragmentation may have been much less common. The reason lies in the limited cooling ability of primordial gas. Modern interstellar clouds contain dust grains and heavier elements that allow gas to cool to very low temperatures. This efficient cooling encourages fragmentation, because colder gas can break into smaller pieces under gravitational instability. In contrast, primordial gas relied almost entirely on molecular hydrogen for cooling. While molecular hydrogen was extremely important, it was not as efficient as the cooling processes available in modern galaxies. As a result, early gas clouds may have remained relatively warm compared with present-day star-forming regions. Warmer gas tends to resist fragmentation. Instead of breaking into many small clumps, the cloud often collapses toward a single dense core. This effect likely played a major role in shaping the first generation of stars. Because fragmentation was limited, the collapsing gas clouds could accumulate large amounts of mass before forming stable stars. In many cases, the central protostar continued accreting gas from its surroundings, growing steadily larger. The result may have been stars far more massive than most stars that form today. Simulations suggest that some of the earlier stars may have reached masses tens or even hundreds of times greater than the mass of our Sun. But before any of those stars could ignite, the gas had to pass through several intermediate stages. The transition from diffuse gas to a dense stellar core was gradual. At first, the gas cloud extended across dozens or even hundreds of light years. The density in these regions remained extremely low by earthly standards, often containing only a few hundred particles per cubic centimeter. Over time, gravity pulled the gas inward, concentrating it within smaller and smaller volumes. As the cloud contracted, the density increased dramatically. Collisions between particles became more frequent. The temperature rose and fell depending on the balance between heating from compression and cooling from molecular hydrogen radiation. Eventually, the central region of the cloud reached densities millions of times greater than the surrounding gas. At that point, the material formed a compact core where gravity dominated almost completely. This core continued collapsing, drawing in additional gas from the surrounding envelope. Although the first protostars were still hidden within thick clouds of gas, the conditions inside those cores were becoming increasingly extreme. Temperatures and pressures climbed steadily as gravity compressed the matter further. The process can be compared to the slow formation of a whirlpool in a calm body of water. At first, the motion is subtle. A slight circular movement appears near the center. As more water flows inward, the motion becomes stronger and more concentrated. In a similar way, the early gas clouds gradually focused their mass into dense central regions where stars would soon form. The entire transformation required patience on cosmic timescales. From the moment gas began collecting inside a dark matter halo to the formation of the first protostellar core, millions of years could pass. Yet in the vast timeline of the universe, this gradual collapse marked a crucial turning point. Diffuse hydrogen and helium gas drifting quietly through space since the Big Bang was finally assembling into the dense structures capable of producing starlight. Deep within those collapsing clouds, the universe was approaching the moment when the first stars would ignite. At some point within those collapsing clouds of primordial gas, a remarkable transformation finally occurred. Gravity compressed the central region so intensely that temperatures began rising to extraordinary levels. As more material fell inward, the density increased further, squeezing the gas tighter and tighter. Eventually, the core of the collapsing cloud became so hot and dense that a fundamental process of nature could begin: nuclear fusion. Nuclear fusion occurs when atomic nuclei collide with enough energy to overcome their electrical repulsion and merge together. When this happens, a small portion of their mass is converted into energy. The relationship between mass and energy was famously described by Albert Einstein in the equation energy equals mass multiplied by the speed of light squared. This equation tells us that even a tiny amount of mass can be converted into a tremendous amount of energy. Inside the first stars, this conversion of mass into energy produced the light that would finally illuminate the universe. These earlier stars belong to a category astronomers call Population 3 stars. The naming system might seem a little backwards at first. Population 3 stars are called that because astronomers originally discovered and classified stars within our galaxy before realizing that earlier generations must have existed. Population 1 stars, such as our Sun, contain relatively high amounts of heavier elements. Population 2 stars are older and contain fewer heavy elements. Population 3 stars represent the very first generation, formed before any heavy elements existed at all. The composition of these primordial stars was extremely simple. They consisted almost entirely of hydrogen and helium, the elements produced during the first minutes after the Big Bang. There were virtually no heavier elements such as carbon, oxygen, nitrogen, or iron. Astronomers refer to these heavier elements collectively as metals, even though many of them are not metals in the everyday sense. In astrophysics, any element heavier than helium falls into this category. Population 3 stars therefore had what scientists call zero metallicity, meaning they contained essentially no heavy elements. This unusual composition had profound consequences for how the first stars formed and evolved. In modern stars, heavier elements help regulate how energy moves through the stellar interior. They also allow gas clouds to cool efficiently before stars form. But the primordial universe lacked these elements entirely. As a result, the first stars formed under very different conditions. Without heavy elements to assist cooling, gas clouds remained relatively warm as they collapsed. This made it harder for the clouds to fragment into smaller pieces. Instead of producing many smaller stars, primordial clouds often continued funneling gas toward a single growing protostar. The young star could therefore accumulate far more mass than most stars forming today. Computer models and theoretical calculations suggest that many population 3 stars may have reached masses tens or even hundreds of times greater than the mass of our Sun. Some simulations suggest upper limits approaching several hundred solar masses. Research by astrophysicist Alexander Heger has been particularly influential in exploring the lives of these massive primordial stars. Heger and his collaborators developed models describing how extremely massive stars evolve when they contain almost no heavy elements. Their work revealed that population 3 stars likely behaved quite differently from most modern stars. Because these stars were so massive, gravity compressed their cores to extremely high temperatures. Fusion reactions occurred at extraordinary rates, producing enormous amounts of energy. As a result, these stars shone with intense brightness. A very massive population 3 star could be millions of times more luminous than our Sun. Even though it formed in a relatively small dark matter halo, its radiation could dominate the entire surrounding region. Yet despite their enormous brightness, these stars were not long-lived. The reason lies in the rate at which nuclear fusion consumes fuel. A star's lifetime depends on how quickly it burns the hydrogen in its core. Massive stars burn their fuel far more rapidly than smaller stars. Our Sun, which is a relatively modest star, is expected to shine for about 10 billion years before exhausting the hydrogen in its core. A star 100 times more massive than the Sun might live only a few million years. Population 3 stars, many of which were extremely massive, likely had lifetimes measured in only a few million years. On cosmic timescales, that is astonishingly brief. These stars appeared, blazed with intense brightness, and then vanished within a tiny fraction of the age of the universe. But during their short lives, they played an enormous role in shaping cosmic history. Because they were so hot, population 3 stars emitted large amounts of ultraviolet radiation. This radiation ionized the surrounding hydrogen gas, beginning the process that would eventually end the cosmic dark ages. Their radiation also influenced nearby gas clouds, heating them and altering how later generations of stars would form. In addition, the immense pressure and temperature inside these stars allowed nuclear reactions to produce elements heavier than helium. Although the earliest stars began with only hydrogen and helium, the fusion reactions in their cores gradually built heavier elements such as carbon, oxygen, and silicon. When the stars eventually died, these elements would be scattered into space. In that sense, population 3 stars were the universe's first factories of chemical complexity. Before they formed, the cosmos contained almost nothing except hydrogen and helium. After they lived and died, the universe began to fill with the heavier elements that would eventually make planets, rocks, oceans, and life possible. Despite their importance, population 3 stars remain extremely difficult to observe directly. Because they existed so early in cosmic history and lived such short lives, none are expected to survive today. Astronomers search for indirect evidence of their existence by studying the chemical signatures they left behind in ancient stars and distant galaxies. Telescopes such as the James Webb Space Telescope are now exploring extremely distant regions of the universe in hopes of glimpsing galaxies that may still contain stars similar to the earliest generation. For now, much of what we know about population 3 stars comes from theoretical modelling and computer simulations. Yet the overall picture is becoming increasingly clear. Within dark matter, halos scattered across the early universe, primordial gas clouds collapsed and formed the first stars. These stars were enormous, brilliant, and short-lived. And for the first time since the cosmic microwave background faded into darkness, the universe was filled once again with light. Deep within the dense cores of the earliest collapsing gas clouds, the temperature continued rising. Gravity compressed the material relentlessly. As gas fell inward, particles collided with increasing frequency, converting gravitational energy into heat. The core grew hotter and denser, its pressure climbing steadily as more matter accumulated. Eventually the conditions crossed a crucial threshold. At temperatures of several million degrees, hydrogen nuclei began colliding with enough energy to overcome their mutual electrical repulsion. When this happened, The nuclei could fuse together, forming heavier elements and releasing enormous amounts of energy. At that moment, the first stars truly came alive. The ignition of nuclear fusion marks the birth of a star. Before this stage, a protostar is simply a collapsing cloud of gas heated by gravitational compression. Once fusion begins in the core, however, the object becomes a self-sustaining source of energy. The physics behind this process was studied in great detail during the 20th century, most notably by the physicist Hans Bethe. In 1938 and 1939, Bethe published groundbreaking work explaining how nuclear fusion powers stars. His research showed how hydrogen nuclei can combine to form helium through a series of nuclear reactions that release vast amounts of energy. In stars similar to our Sun, this process occurs primarily through a sequence known as the proton-proton chain. In more massive stars, a different set of reactions called the carbon-nitrogen-oxygen cycle can dominate. The earlier stars likely relied mostly on the proton-proton chain at first, since they contained almost no heavier elements to support other fusion pathways. Regardless of the specific reaction pathway, the underlying principle remains the same. When hydrogen nuclei fuse into helium, a small fraction of their mass is converted into energy, according to Einstein's famous relationship between mass and energy. Energy equals mass multiplied by the speed of light squared. Although only a tiny portion of the mass is transformed, the speed of light is an extremely large number. When it is squared, the resulting energy becomes enormous. Inside a star, this energy pushes outward as radiation and heat. That outward pressure balances the inward pull of gravity. When the two forces reach equilibrium, the star becomes stable. For the first time since the cosmic microwave background faded into darkness, the universe gained a new source of light. But this light was very different from the ancient glow left behind by the Big Bang. The cosmic microwave background was diffuse and nearly uniform, filling all of space with a faint afterglow. The light produced by the first stars, by contrast, came from discrete points scattered across the universe. Each new star was like a cosmic lantern igniting within the darkness. These stars were also extraordinarily bright. Because many population 3 stars were extremely massive, their cores reached tremendous temperatures. Massive stars burn their nuclear fuel at extraordinary rates, producing immense amounts of radiation. A single massive primordial star could shine with a luminosity millions of times greater than the Sun. And because these stars were so hot, much of their radiation was emitted in the form of ultraviolet light. Ultraviolet radiation carries far more energy than visible light. When ultraviolet photons encounter neutral hydrogen atoms, they can strip electrons away from those atoms, turning them back into charged particles. This process is known as ionization. As the first stars ignited, their ultraviolet radiation began interacting with the surrounding hydrogen gas that filled the universe. Regions of space near these stars became filled with ionized hydrogen. Astronomers refer to these zones as ionized bubbles. Inside such bubbles, the radiation from the star had enough energy to remove electrons from hydrogen atoms, creating a plasma similar to the state of matter that existed before recombination. Outside these bubbles, the universe remained filled with neutral hydrogen. Over time, as more stars formed across the cosmos, these ionized regions grew larger and began overlapping with one another. This gradual transformation marked the beginning of an important era in cosmic history. Astronomers refer to this era as cosmic dawn. Cosmic dawn represents the period when the first luminous objects appeared in the universe, after the long darkness that followed recombination. The name is fitting. Just as dawn on Earth marks the gradual return of sunlight after night, cosmic dawn marked the universe's transition from darkness to illumination. The process was not instantaneous. The first stars likely formed hundreds of millions of years after the Big Bang, scattered across distant regions of the cosmic web. Their light slowly spread outward, illuminating the surrounding gas. At first, these stars appeared in isolation, separated by vast distances. But as time passed, more stars formed inside growing dark matter halos. Small clusters of stars began appearing within the earliest galaxies. Their combined radiation produced ever larger regions of ionized gas. In many ways, the first stars were like sparks igniting within a dark forest. Each spark illuminated only a small region at first, but as more sparks appeared, the darkness gradually receded. These stars also had dramatic effects on their immediate surroundings. The intense radiation they emitted heated nearby gas, changing how future clouds collapsed and formed stars. Ultraviolet photons could break apart molecular hydrogen, altering the chemistry that allowed primordial gas to cool. In some cases, the radiation from one early star may have prevented nearby gas clouds from forming additional stars for a time. In other cases, shock waves and radiation pressure may have triggered new collapses elsewhere. The early universe was becoming an active and evolving environment. Light was spreading, chemistry was becoming more complex, and the once silent cosmos was beginning to glow once again. Although individual stars lived only a few million years, new generations began forming as earlier ones died. Over time, the number of luminous objects increased. The darkness that had dominated the universe for hundreds of millions of years was slowly being replaced by scattered islands of light. The universe had entered a new phase. The long night following the Big Bang was ending, and the first glimmers of cosmic dawn were beginning to shine. As the first stars began shining across the young universe, their influence extended far beyond their immediate surroundings. The intense ultraviolet radiation produced by these stars interacted directly with the vast ocean of neutral hydrogen that still filled most of space. Each energetic photon carried enough energy to remove an electron from a hydrogen atom, turning that atom into a positively charged ion. This process is called ionization. When hydrogen atoms lose their electrons, they no longer remain neutral. Instead, the gas becomes a plasma once again, similar in some ways to the state that existed before recombination hundreds of thousands of years after the Big Bang. But unlike the earlier plasma phase, this new ionization did not occur everywhere at once. It spread gradually. The transformation of the universe from neutral hydrogen back into ionized plasma is known as cosmic reionization. The term may sound slightly confusing at first. The universe was originally ionized during its earliest moments, long before atoms existed. Later, when the universe cooled, recombination allowed electrons and protons to combine into neutral hydrogen. Reionization refers to the later period when radiation from the first stars and galaxies once again stripped electrons from hydrogen atoms. The earlier stages of reionization began locally. When a massive primordial star ignited, its ultraviolet radiation flooded the surrounding gas. Hydrogen atoms in the immediate region absorbed this radiation and became ionized. As a result, a glowing sphere of ionized hydrogen formed around the star. Astronomers sometimes refer to these regions as ionization bubbles. Within these bubbles, hydrogen existed as a plasma. Outside them, the universe still consisted mostly of neutral gas. As more stars formed across the cosmos, new bubbles appeared. Some bubbles expanded as additional stars ignited inside them. Others began overlapping with neighboring bubbles. Gradually, the ionized regions grew larger and more numerous. Over time, these expanding zones of ionized hydrogen began merging together. The once neutral universe slowly transformed into an environment filled with ionized gas. This transformation took hundreds of millions of years. During this long interval, the universe contained a complex patchwork of regions. Some areas were filled with ionized plasma surrounding clusters of young stars and galaxies. Other areas remained mostly neutral, still waiting for radiation to reach them. Astronomers have found several ways to detect evidence of this transition. One of the most important clues comes from an observational feature known as the Gunn-Peterson Trough. The Gunn-Peterson Trough was first identified in the 1960s by astronomers James Gunn and Bruce Peterson. While studying the spectra of distant quasars, they noticed a distinctive pattern in the absorption of light. Quasars are extremely luminous objects powered by supermassive black holes at the centers of galaxies. Because they shine so brightly, astronomers can observe them even across vast cosmic distances. As light from a distant quasar travels toward Earth, it passes through enormous stretches of intergalactic space filled with hydrogen gas. If that hydrogen is neutral, it absorbs specific wavelengths of light, particularly those associated with the hydrogen-Lyman alpha transition. When this happens, the spectrum of the quasar shows a strong region of absorption, where light has been removed. If the hydrogen is mostly ionized, however, much less absorption occurs. The Gunn-Peterson Trough refers to a broad region in a quasar spectrum where light is almost completely absorbed by neutral hydrogen. Its presence indicates that the light passed through large regions of neutral gas. By observing quasars at different distances, astronomers can see how the amount of absorption changes over cosmic time. These observations reveal that the early universe contained significant amounts of neutral hydrogen, but at later times, the amount of neutral gas decreased dramatically. This pattern provides strong evidence that cosmic reionization occurred during the first billion years after the Big Bang. Understanding the detailed physics of this era has become a major focus of modern cosmology. Researchers such as Abraham Loeb and Stephen Furlanetto have played important roles in developing theoretical models of reionization. Their work examines how radiation from early stars, galaxies, and possibly quasars spread through the intergalactic medium. One of the key insights from these studies is that reionization was not uniform across the universe. Instead, it occurred in a patchy and uneven manner. Regions containing many galaxies experienced reionization earlier because they produced larger amounts of ultraviolet radiation. Areas with fewer stars remained neutral for longer periods. As a result, the universe during this era resembled a mosaic of ionized and neutral regions. Imagine a frozen lake slowly melting during spring. Small patches of open water appear first where sunlight and warmth are strongest. Over time, these patches grow and connect with one another until the entire surface becomes liquid. Cosmic reionization unfolded in a somewhat similar way. Islands of ionized gas appeared around the earliest galaxies. These islands expanded and merged until most of the hydrogen between galaxies became ionized. The completion of this process marked the end of the cosmic dark ages. Once hydrogen across much of the universe became ionized, ultraviolet light from stars could travel far more freely through intergalactic space. The universe had effectively become transparent again to high-energy radiation. From that point onward, galaxies and stars illuminated the cosmos on an ever-increasing scale. The once silent universe was now alive with light. Yet this transformation did not erase the earlier chapters of cosmic history. The structures that formed during the Dark Ages, dark matter halos, collapsing gas clouds, and the first massive stars had already set the stage. Reionization simply revealed a universe that was becoming increasingly active and complex. Across vast distances, radiation from countless young stars continued reshaping the intergalactic medium. The darkness that once filled the cosmos was gradually retreating, and in its place, the light of the first galaxies was beginning to spread across the universe. The first stars illuminated the universe, but their brilliance did not last forever. Because many of these primordial stars were extremely massive, they lived fast and ended their lives quickly. The nuclear reactions in their cores burned through hydrogen at astonishing rates, producing immense amounts of energy, but also exhausting their fuel in only a few million years. For a star, the balance between gravity and nuclear energy is delicate. Throughout most of a star's life, gravity pulls matter inward, while the pressure produced by nuclear fusion pushes outward. As long as these two forces remain in equilibrium, the star remains stable, but eventually the fuel that sustains this balance begins to run out. When hydrogen in the core becomes depleted, fusion reactions slow down. Without enough energy pushing outward, gravity begins compressing the core more strongly. Temperatures and pressures rise, allowing new fusion reactions to begin. Inside massive stars, this sequence continues through a remarkable chain of nuclear transformations. Hydrogen fuses into helium, helium fuses into carbon, carbon can fuse into oxygen, neon, magnesium, and eventually heavier elements. These nuclear reactions take place in successive layers within the star, somewhat like the layers of an onion. The physics behind these transformations was explored in depth in the late 1950s through a landmark scientific paper often referred to as the B2FH paper. The initials stand for the authors Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. Their paper, published in 1957, provided one of the first comprehensive explanations of stellar nucleosynthesis, the process by which stars create heavier elements through nuclear reactions. Before this work, astronomers understood that stars produced energy through fusion, but the details of how different elements formed were still uncertain. The Burbidge, Fowler, and Hoyle study showed how stars act as cosmic furnaces, gradually building elements heavier than hydrogen and helium through successive stages of nuclear fusion. Inside massive stars, the core temperature can eventually reach billions of degrees. At such extreme conditions, fusion reactions produce elements including carbon, oxygen, silicon, and iron. Each stage requires higher temperatures and pressures than the one before it. But this chain of reactions cannot continue indefinitely. iron marks a crucial turning point in stellar physics. Unlike lighter elements, fusing iron nuclei does not release energy. Instead, it consumes energy. When a star's core becomes dominated by iron, fusion can no longer support the star against gravity. At that moment, the core collapses. The collapse occurs extremely quickly, often within a fraction of a second. As the core contracts, densities become enormous. Electrons are squeezed into protons, producing neutrons and a burst of neutrinos. The outer layers of the star then rebound violently from the collapsing core. The result is one of the most energetic events in the universe, a supernova explosion. During a supernova, a star can briefly shine brighter than an entire galaxy. Vast amounts of energy are released, and the outer layers of the star are hurled into space at tremendous speeds. These explosions do more than simply destroy stars. They also manufacture and distribute many of the heavy elements that make up the modern universe. When the shock wave from the supernova moves outward through the star's layers, it triggers additional nuclear reactions. These reactions produce elements heavier than iron, including gold, uranium, and many other metals. The explosion then scatters these elements into surrounding space. Gas enriched with these newly created atoms spreads outward into the interstellar medium, mixing with the hydrogen and helium left over from earlier cosmic epochs. This process gradually transforms the chemical composition of the universe. The earliest stars began with almost no heavy elements. After the first supernovae occurred, the cosmos slowly became enriched with new materials. Later generations of stars would form from this enriched gas, incorporating heavier elements into their structures. For the most massive population 3 stars, the final explosions may have been even more dramatic. Some extremely massive primordial stars are thought to have ended their lives through an event known as a pair instability supernova. This type of explosion occurs when the star's core reaches extremely high temperatures, often exceeding several billion degrees. At such temperatures, energetic photons can transform into pairs of particles known as an electron and a positron. This process reduces the radiation pressure supporting the star. As radiation pressure drops, the core suddenly becomes unstable. Gravity causes the core to contract rapidly, triggering a runaway series of nuclear reactions. These reactions release enormous energy, completely disrupting the star. Unlike many other supernovae, a pair instability supernova may leave no remnant behind. The entire star can be blown apart, dispersing all of its material into surrounding space. These explosions may have produced some of the earliest heavy elements in the universe. Although astronomers have not directly observed a population 3 star exploding in this way, theoretical models strongly suggest that such events occurred in the early cosmos. Evidence supporting these models comes from studying ancient stars in our own galaxy. Some extremely old stars contain unusual patterns of chemical elements that match the predicted signatures of pair instability supernovae. These ancient stars act as chemical fossils, preserving traces of events that occurred billions of years ago. Through them, astronomers can glimpse the violent deaths of the first generation of stars. The importance of these explosions cannot be overstated. Before the first supernovae occurred, the universe was chemically simple. Hydrogen and helium dominated almost everything. Complex chemistry was impossible because the necessary elements did not yet exist. But after the first stellar explosions, the cosmos began to change. Carbon became available for building organic molecules. Oxygen could combine with hydrogen to form water. Silicon and iron could eventually form rocky planets. In other words, the violent deaths of the first stars made the universe far more interesting. From the ashes of those early explosions came the ingredients needed for galaxies, planets, and eventually life. The first stars had illuminated the darkness, and when they exploded, they began filling the universe with the elements that would shape everything that followed. When the first massive stars exploded, they did more than end their own lives. They permanently changed the chemistry of the universe. Before those explosions, the cosmos was almost chemically uniform. Hydrogen and helium dominated nearly everything, with only tiny traces of lithium left over from the earliest minutes after the Big Bang. The ingredients needed for complex chemistry simply did not exist. But when the first supernovae scattered their material into space, the universe gained new elements. Carbon, oxygen, silicon, magnesium, iron, and many others began spreading outward through the interstellar medium. These elements mixed gradually with the surrounding hydrogen and helium gas drifting between galaxies. Over time, this process began transforming the cosmic environment. Astronomers describe this transformation using the term cosmic chemical evolution. Cosmic chemical evolution refers to the gradual enrichment of the universe, with heavier elements created by stars. Each generation of stars forms from gas left behind by earlier generations. As stars live and die, they produce and disperse new elements, slowly increasing the chemical complexity of the cosmos. In the earliest eras, stars formed from almost pure hydrogen and helium. Later generations formed from gas containing increasing amounts of heavier elements. This progression continues even today. The Sun, for example, formed about 4.5 billion years ago from gas that had already been enriched by many earlier stellar generations. Roughly 2% of the Sun's mass consists of elements heavier than helium. By the standards of the earliest universe, that makes the Sun relatively metal-rich. Tracing this gradual enrichment across cosmic history is one of the most fascinating challenges in astronomy. One powerful approach involves studying extremely old stars that still exist today. Some stars formed very early in the history of our galaxy, at a time when heavy elements were still rare. Because these stars contain so few metals, astronomers refer to them as metal-poor stars. In extreme cases, these stars contain only a tiny fraction of the heavy elements found in the Sun. Their chemical compositions closely resemble the gas that existed shortly after the first supernovae enriched the universe. Studying these stars is a bit like examining fossils from the early history of life on Earth. For this reason, the field devoted to investigating these ancient stars is often called stellar archaeology. Stellar archaeology aims to reconstruct the chemical history of the universe by analysing the elemental fingerprints preserved in old stars. Every star contains a record of the gas from which it formed. By measuring the abundance of different elements inside a star, astronomers can infer the kinds of stellar explosions that enriched the gas long ago. Some of the most detailed work in this field has been carried out by astronomer Anna Friebel, whose research focuses on identifying and analysing extremely metal-poor stars in the Milky Way. Friebel and her collaborators search for ancient stars using large telescopes, capable of measuring stellar spectra with extraordinary precision. A stellar spectrum reveals the wavelengths of light absorbed and emitted by elements within a star's atmosphere. Each element produces a distinctive pattern of absorption lines. By studying these patterns, astronomers can determine how much carbon, iron, magnesium, calcium, and other elements are present. In some of the oldest known stars, the iron content can be more than 100,000 times lower than the iron content of the Sun. Stars with such low metallicity likely formed from gas enriched by only one or a few earlier supernovae. Their chemical compositions preserve clues about the first generations of stars that lived and died billions of years ago. Through these studies, astronomers have begun reconstructing the sequence of events that transformed the early universe. The earliest stars produced the first heavy elements through nuclear fusion and supernova explosions. These elements mixed into the surrounding gas, gradually increasing the metal content of interstellar clouds. Once heavy elements were present, star formation began to change. Metals and dust grains greatly improved the cooling efficiency of gas clouds. When gas can cool more effectively, it can fragment into smaller clumps during gravitational collapse. This fragmentation leads to the formation of many smaller stars rather than a few extremely massive ones. In other words, the presence of heavy elements altered the typical mass of newly forming stars. The earlier stars were often extremely massive because cooling was limited. Later generations formed with a wider range of masses, including stars much smaller than the Sun. Some of these smaller stars have lifetimes longer than the current age of the universe. That is why a few ancient stars still exist today, quietly shining in the halo of the Milky Way, while preserving chemical memories from the earliest eras of cosmic history. Cosmic chemical evolution also laid the groundwork for an entirely new category of astronomical objects: planets. Planets require solid materials such as silicon, oxygen, iron, carbon, and other heavy elements. Without these ingredients, it would be impossible to build rocky worlds, icy moons, or complex atmospheres. In the earliest universe, planets could not exist because the necessary elements had not yet been created. But as supernovae enriched the gas in galaxies, those elements gradually accumulated. Dust grains began forming within interstellar clouds. These grains clumped together inside rotating disks around young stars, eventually forming planetesimals and planets. In this way, the violent deaths of the earlier stars set the stage for entirely new cosmic structures. galaxies gained richer chemistry, stars formed with more diverse compositions, and eventually planetary systems like our own solar system began appearing throughout the universe. The atoms that make up Earth, its oceans, its atmosphere, and even our own bodies were once forged inside ancient stars. Those atoms were scattered through space by supernova explosions long before our Sun existed. By studying the chemical fingerprints preserved in ancient stars, astronomers are slowly uncovering the story of how the universe transformed from a simple mixture of hydrogen and helium into the chemically rich cosmos we see today. A story written not in words but in the elements themselves. As the first stars ignited across the young universe, they did not remain isolated for long. Stars formed inside dark matter halos, and those halos were rarely alone. Gravity continued shaping the cosmic web, pulling halos toward one another along the vast filaments of dark matter that stretched across space. When two halos approached each other, their mutual gravity often caused them to merge. This merging process gradually brought together many small star-forming regions. Clusters of stars began gathering within shared gravitational environments, forming larger and more complex systems. Over time, these growing systems became the earliest galaxies. The galaxies that emerged during this era were not yet the grand spirals or enormous ellipticals we see in the modern universe. They were smaller and more irregular, often containing only a few million stars rather than the hundreds of billions found in mature galaxies like the Milky Way. Yet even these primitive galaxies represented a dramatic step forward in cosmic organization. For the first time, stars were no longer scattered randomly across space. Instead, they existed within coherent systems bound together by gravity. Gas clouds, stars, and dark matter interacted within shared structures, forming the first recognizable galactic environments. The formation of these early galaxies followed the same hierarchical pattern that shaped dark matter halos. Small halos merged to create larger halos. Gas clouds inside them collided and mixed. Star clusters formed, evolved, and sometimes merged with neighboring clusters. Each merger brought new gas and stars into the growing system. Over hundreds of millions of years, this gradual assembly process produced galaxies of increasing size and complexity. Understanding how this transformation occurred has been one of the central goals of modern astronomy. Observing the earliest galaxies directly is extremely challenging because they lie at enormous distances. The light from these galaxies began its journey toward Earth billions of years ago, when the universe itself was still very young. But recent advances in telescope technology have begun revealing these ancient systems. One of the most powerful tools for exploring the early universe is the James Webb Space Telescope. Launched in 2021 by the National Aeronautics and Space Administration, the European Space Agency, and the Canadian Space Agency, this telescope was designed specifically to observe extremely distant galaxies. Because the expansion of the universe stretches light toward longer wavelengths, radiation emitted by the earliest galaxies arrives at Earth primarily in the infrared portion of the spectrum. The James Webb Space Telescope is optimized to detect this infrared light with extraordinary sensitivity. Within its first years of operation, the telescope began identifying galaxies that existed when the universe was only a few 100 million years old. Some of these galaxies appear surprisingly mature for such an early period. Astronomers have detected compact systems containing large numbers of stars, suggesting that galaxy formation may have proceeded more rapidly than some earlier models predicted. Each new observation helps refine our understanding of how the first galactic systems emerged. Theoretical work has also played an important role in exploring this early era of cosmic history. Astrophysicist Priyamvada Natarajan has conducted extensive research into the formation of early galaxies and the massive black holes that sometimes form within them. Her work examines how supermassive black holes, objects containing millions or billions of times the mass of the Sun, could appear relatively quickly in the young universe. These black holes power extremely bright objects known as quasars, which can outshine entire galaxies. Natarajan and her collaborators have studied several possible pathways for the formation of these early black holes. One possibility involves the direct collapse of massive gas clouds inside young galaxies. Another possibility involves the remnants of massive primordial stars that later grow by accreting surrounding gas. Whichever mechanism proves most important, the presence of massive black holes suggests that galaxy formation was already underway on significant scales during the universe's first billion years. Meanwhile, dark matter halos continued merging and evolving. The halos hosting early galaxies gradually combined with neighboring halos, creating larger gravitational systems. As these halos merged, the galaxies within them often interacted or collided. Galactic mergers are powerful events. When two galaxies approach one another, their mutual gravity can distort their shapes, triggering bursts of star formation as gas clouds collide and compress. Over time, repeated mergers can completely transform a galaxy's structure. The earliest galaxies likely experienced many such interactions as they assembled within the growing cosmic web. Through these mergers and accretion processes, small protogalaxies gradually evolved into larger systems. Gas continued flowing along dark matter filaments, feeding galaxies with fresh material for star formation. New generations of stars formed within dense clouds enriched by earlier supernova explosions. Gradually, the universe began filling with increasingly complex galactic structures. What began as isolated stars inside small dark matter halos was evolving into organized systems containing stars, gas, dust, and sometimes massive black holes. These early galaxies were still primitive compared with the galaxies we observe today. Their shapes were often irregular, their stars were young and energetic, their chemical compositions remained relatively simple compared with modern galaxies. But they represented a crucial transition. The universe was moving from a stage dominated by individual stars toward a cosmos filled with vast stellar systems. Galaxies became the fundamental building blocks of large-scale cosmic structure. Within them, stars formed, evolved, and died. Gas circulated through cycles of collapse and explosion. Heavy elements accumulated over time, and within some galaxies, planetary systems would eventually begin to appear. The quiet, dark ages that followed the Big Bang had given way to a universe filled with growing islands of starlight. Those islands were the first galaxies, slowly assembling across the expanding cosmos. Even though the cosmic dark ages ended billions of years ago, astronomers are still searching for ways to observe that era directly. Studying such an early period presents a difficult challenge. The universe was filled mostly with neutral hydrogen gas, and there were very few bright objects emitting visible light. Traditional telescopes that observe stars and galaxies cannot easily detect this quiet phase of cosmic history. Yet the hydrogen atoms that filled the early universe left behind a subtle signal. This signal arises from a property of hydrogen known as the 21 centimeter line. A hydrogen atom consists of a proton and an electron. Both of these particles possess a property called spin, which behaves somewhat like a tiny magnetic orientation. The relative alignment of the proton spin and the electron spin can change between two different configurations. When the spins flip from a higher energy alignment to a lower energy alignment, the atom releases a photon. The wavelength of this photon is approximately 21 centimeters. Although the energy involved in this transition is extremely small, the vast abundance of hydrogen atoms in the universe means that the signal can still be detected with sensitive radio telescopes. In the early universe, before and during the formation of the first stars, neutral hydrogen gas filled enormous regions of space. The 21 centimeter radiation produced by those atoms carries information about the temperature, density, and motion of the gas during the cosmic dark ages. By detecting this radiation, astronomers hope to map the distribution of hydrogen across the early universe. However, observing the signal is far from easy. Over billions of years, the expansion of the universe has stretched the wavelength of the 21 centimeter radiation far beyond its original value. By the time the signal reaches Earth from the earliest cosmic epochs, it has been shifted to much longer radio wavelengths. These wavelengths fall within frequency ranges that are easily contaminated by radio interference from human technology, as well as emissions from our own galaxy. Extracting the faint cosmological signal from this noisy background requires extremely sensitive instruments and careful analysis. One experiment that attracted significant attention is known as EDGES, which stands for the Experiment to Detect the Global Epoch of Reionization Signature. This project operates a radio antenna in the remote desert of Western Australia, far from most sources of radio interference. In 2018, the EDGES team announced that they had detected an unexpected absorption feature in the radio spectrum corresponding to a time roughly 180 million years after the Big Bang. If confirmed, this signal could represent the first direct evidence of hydrogen gas interacting with radiation from the earlier stars. The results sparked intense interest within the astronomical community. However, interpreting the signal has proven difficult. Other researchers have questioned whether the feature truly represents a cosmological signal or whether it might arise from instrumental effects or foreground interference. Even so, the experiment demonstrated that detecting radiation from the cosmic dark ages may be within reach of modern technology. Theoretical work has also helped clarify what astronomers should expect to see. One researcher who has contributed significantly to this effort is astrophysicist Renan Barkana. Barkana has studied how the radiation from the first stars and galaxies interacts with hydrogen gas during the cosmic dawn. His work examines how ultraviolet light and X-ray radiation influence the temperature of hydrogen gas and alter the strength of the 21 centimeter signal. By modeling these processes, scientists can predict how the signal should change as the first stars form and begin heating the surrounding gas. These predictions guide the design of new experiments, searching for the faint signatures of early cosmic history. Several large observational projects are currently under development to explore this era in far greater detail. One of the most ambitious of these is the Square Kilometre Array, often abbreviated as the SKA. The Square Kilometre Array will be one of the largest radio telescope facilities ever constructed. It will consist of thousands of antennas spread across vast regions of South Africa and Australia. When completed, the combined collecting area of these antennas will approach 1 square kilometre, providing extraordinary sensitivity to faint radio signals. The telescope is designed to map the 21 centimetre emission from hydrogen across enormous volumes of space. With this capability, astronomers hope to create three-dimensional maps showing how hydrogen gas evolved during the cosmic dark ages and the era of Orionization. Such maps could reveal where the first stars formed, how radiation spread through the early universe, and how large-scale structures developed over time. In essence, the Square Kilometre Array may allow scientists to watch the universe gradually emerge from darkness. The project represents a major international collaboration involving scientists and engineers from dozens of countries. Although the telescope is still under construction, its future observations promise to transform our understanding of the earliest chapters of cosmic history. Other experiments are also contributing to this effort. Radio observatories such as the Hydrogen Epoch of Orionization Array and the Low Frequency Array are already collecting data that may contain traces of early hydrogen signals. Each of these projects pushes the limits of observational astronomy, searching for signals that are incredibly faint and easily overwhelmed by foreground noise. Yet with each new instrument, our ability to probe the ancient universe improves. For most of human history, the cosmic dark ages were completely invisible to us. The earlier stars had long since vanished, and the faint radiation from neutral hydrogen seemed beyond the reach of observation. But modern astronomy is slowly changing that picture. Through radio observations, sophisticated simulations, and powerful telescopes, scientists are beginning to uncover the hidden story of the universe's earliest epochs. The Dark Ages are no longer entirely dark to us. Bit by bit, the signals from that distant time are reaching our instruments, carrying whispers from a universe that existed before the first stars lit the sky.